So I'm Alex. I'm here today to talk with you guys about a project that I had the opportunity to work with these colleagues at Tetra Tech, which is the company I work for. And we worked on a project called From Cave Buffer Zones to Protected Areas, Speleology Data Management with Free and Open Source Software. A little background about me. I am not from a computer science background. I am an environmental engineering, so I do not have a lot of knowledge in programming and developing as you guys and the amazing work that I have seen here. But I'm gonna try to show the project that we worked over the past year. All right, so a little bit about speleology. Speleology is a field of study that relies heavily on the accurate mapping and analysis of spatial data. So spatial data is key because knowing where those speleological formations happens, it's important. The convergence of general purpose FOSS tools with speleology specific applications offers unique opportunities for developing solutions in cave exploration and research. We have been participating in meetings here and seeing that FOSS is being applied to many areas, and speleology could be one of them, and that's my main point here, trying to present to you guys. And FOSS is already being used to other projects like geological hazards, hydrological vulnerability, and why not apply it to speleological studies? And my last point here in the introduction, it's about SECAVI, which is a national repository for caves, speleological data, and I do not know what kind of technology they're using in the background to store that kind of data and to share it, but I would be glad to connect afterwards and talk if there are any folks here from ICMBio, which is the federal agency that administer that kind of information. All right, so here in Brazil we have a specific legislation about those speleological formations that mandates guidelines for activities near those formations. And it is mandatory to protect those ecosystems and the surrounding of it. So precisely locating these formations is really important, and that's what comes in place here. So location is key, and that's what I'm going to be talking about most of the presentation. And another thing is 250 meters buffer zone around caves is set as soon as the cave is identified in the field. This is a default predefined area in the legislation. I'm not here to talk if it is correct or not. I'm just mentioning what is the law. And those areas can be altered based on the speleological studies that happened throughout the course of knowing the cave and its importance to the environment. So 2 objectives here. The first one is to exhibit a existing software architecture called EspeleoVale that uses Postgres, PostGIS for speleological data management, PostGIS for spatial analysis, and Geoserver and MapStore2 for data visualization. And the second one is to demonstrate a new development that we conquered the past semester within that architecture. Great, so just to get everybody on the same page, the main steps of a speleological study starts with the prospection, which is like, oh, I want to install a new unit, a new site, and we need to find if there are any occurrences of caves in that area. So the prospection is going to the field, walking through that area, and knowing if there are any occurrences of speleological formations. And if occurs, the main information gathered at that moment is just, like a location, a point of these formations and some attributes. And then identified, it comes the other studies needed. The second one is the topography. So that point now gonna have a more accurate point because you come back with more equipment, more accurate equipment, and you turn that point also to a 2D representation. Now you have the geometrical features of the cave. Given that you jump to the geological, geographical, biological, cultural heritage studies, and I'm not going to go into them, not going to detail them here, is not the point, but they're important to classify the cave. And classification in the cave means like what is the relevance cave to the environment. And that can be like, this cave is not very important because it happens, it has happened in other places, or this cave is very important because it has a rare species. It has some cultural heritage, like some people used to come here back in the days. So that's important to know that the relevance is attributed by the studies before, the step before. And then any kind of economic activity, once you know what, if they find those caves, what they're gonna do with it, like if they can suppress those caves by meaning compensating them somewhere else because the legislation allows them to do that given the prior relevance identified, or if they need and gonna preserve those caves. So this is like pretty much the roadmap of this speleological study. And talking about the spatial data object, which is the main point here. So as I mentioned, in the prospection phase, it's just identify the cave, so it's a coordinate. And then it changes to a more accurate coordinate, so it's the topography coordinate. And that coordinate is updated to a 2D representation of the cave, which is a polygon, but it also could be a multi-polygon because caves can have holes within it. All right, great. So here's an example, because so far I only have been talking about, and you could be imagining, but an example is great to show that here we have the yellow dot, which is the initial coordinate, the green dot, which is the topographical coordinate, and the polygon representing in the gray here, which is the 2D representation. Do you guys remember I mentioned the 250 meters? It is those regions like buffered here. So for each one, it is good to know what is the extension around the cave that you need to be protecting until you reach out all these studies and you can then define a specific region. I'm gonna call it here restricted area. So I'm gonna be mentioning, which is this red area. It doesn't need to be within that buffer, it can go beyond the buffer, and this is just hypothetical. I'm just showing an example here. So those buffers can be altered to a specific region. So knowing the process and following these steps, it's pretty important in this kind of studies. All right, so the software architecture that I mentioned, it's called SpeleoVale, and it is a software as service hosted on Amazon. Oh, sorry. Hosted on Amazon. And it uses like mainly Golang, Angular, and React for the front-end development, APIs, that kind of thing. And in the back end uses Postgres and PostGIS as the database. With that database, we are able to publish it through Geoserver. So now we have geoservices that can be used and seen with a web application, which we're using MapStore here, also developed by GeoSolutions. And on the right part here of this slide, I have just a snapshot of the MapStore showing SpeleoVale displaying its valley caves, which occurs in both regions that Vale operates the most, which is Pará and Minas Gerais here in Brazil. And there are more than 6,000 caves already cataloged in this database, so you guys can imagine all the work done here. And here's a snapshot of the software architecture. I'm just displaying here for an example, and it's pretty simple, straightforward to either register information or to visualize information. All right, you guys might be curious about the database. I brought here a simplified version of it because it's pretty extensive and I could be presenting 40 minutes of the database. But I'm gonna show here, the tables that we're mainly using for the purpose of this new development that we achieved. And you can see like there are the caves table, the polygon table, the initial coordinates table, the relevance, and they're connected. So relational database comes in hand here to help us achieve what we wanted, which are connect this information. And also you can see the geometry representation within the database, which is allowed by PostGIS, which is great because before we used to do this separately. We would have the alphanumeric data stored in a relational database and the spatial data stored in a shapefile or other vector format. All right, so now talking about the new feature that we developed recently, the user requested us to, based on an insertion of a region of interest, to return not only the caves that are associated with that area, but also what is associated, which geometries are, connecting, intersecting, differencing from that region of interest. And we developed it in 3 steps. It's pretty simple. It's done in the back end in PostGIS using spatial analysis. And the first step, great. First step is to verify, because the user doesn't provide a number protocol or an identification for this region of interest. We just verify and tell the user, like, you might have entered this area before, by just running an intersection and saying like, oh, this is the level of intersection with the existing database that we have. It's just a verification step, and then when the verification is done, we have the analysis. And the analysis is run by a trigger in the database, and it's pretty simple as well. It's just like a bunch of spatial functions running intersection, union, difference, and I'm gonna talk a little bit about this. So the insertion occurs in the SpeleoVale system. It's pretty straightforward. It's through its upload button. Don't need to waste time on this slide. All right, the overlap, as I mentioned, is just a simple function checking for intersection with the existing database, existing table in the database. And it comes to the spatial analysis. Here the code is longer, but don't worry about it. It's not very complicated. It's just like a bunch of spatial functions, as I mentioned: intersection, difference, union, performing the spatial analysis. And I'm going to show the results. So for the purpose of FOSS4G here, we created a study case, which is a hypothetical scenario with like 5 caves and a region of interest near Belém. So here's just a snapshot of MapStore showing those caves, the attribute table. And here I just want to mention, like, it's 5 caves. So 1, 2, and 3 are clustered here together. They're near each other. So this is the example. And using Geoserver and SLD formatting, I don't know if you guys have heard that style format before, we were able to have a table, a view in the database, and have multi-geometry columns. So we represented this as one feature. So this is cool. It's kind of a group layer, and if we want to filter, let's say this cave right here, it filters not only the initial coordinate, but the initial, the topography, the buffer around it. It's pretty neat. Going forward, we have hypothetically defined the restricted areas for these caves. So it's the red here. And one thing that I forgot to mention, it's that a cave can have its own defined restricted area, or a defined restricted area can group more than one cave. So it brings us the one-to-many relationship, which is a difficulty that we had here. So with that, we decided to have the analysis region of interest oriented, meaning that the region of interest is going to be our output and everything going to be associated with it. This is the main result. So this big polygon here is a hypothetical lab that they want might to construct. And here you have the caves, and the red here is the restricted areas. And now you have the spatial analysis performed. And as I mentioned, that is stored in the database as a table with many geometry columns, which allow us to represent all these areas here that the user might know. So he can go back and design the project again and say like, oh, all right, I'm gonna shift this, I'm gonna move those vertex a little bit north, and then run it again. So it's really interesting analysis, and it gives us the result of, the merged buffers with the union here represent all of this. The orange here is the difference between what does not intersect the region of interest. And the green here is what intersect the region of interest. So it gives those geometries readily available to the user so he can visualize it, and also like the table with the areas, so it gives like an idea of like, oh, how much is intersecting. So this is the structure of the table that I mentioned, like with the caves associated with it, the geometries, and the areas stored in the database. All right, so it comes, I think I passed too fast. Maybe I speak too fast. All right, so it comes to the conclusion of the work that the integration of FOSS technologies allowed increase the potential for managing and visualizing speleological data. The ready available spatial analysis facilitates informed decision making, and that's what we're trying to achieve here, to put the environmental agenda in the first place for the client, so the client has those numbers, those visualizations in the hand, so they could talk to their executives and make informed decisions, not only after like the damage is done and they have expanded their operations. So this is really important. And the future of speleology, at least for us, is the adoption of innovative solutions, and we're learning so much here already that could be applied to this software architecture that I mentioned. And this is crucial for sustainable exploration and preservation of these environments. Some people that I would like to acknowledge here. First, everybody that collaborated in this work. I also want to thank Tetra Tech and Vale for sponsoring my presence here and like supporting me to come and present this work. Fabrício Lisboa for sharing with me this template, this PowerPoint template. The FOSS4G committee for reading, evaluating this work, and allowing us to come and contribute in this event. And also INPE and EFPA for hosting us here in Belém. So thank you very much for everything. This is my contact information, and I think it's time for some Q&A.